Assalamualaikum. Welcome back to Sir K Labs Physics and Chemistry tutorial for high school students. In today's episode, we solve problems involving optical instruments. How is geometric optics applied in a magnifying glass, a refracting telescope, and an optical microscope? Join me till the end of this video. Watch and learn. First in our list of optical instruments is the magnifying glass, which is simply a converging lens or a double convex lens. Its angular magnification, denoted as capital M, is equal to the angular size theta prime, all right, of the image with the magnifying glass divided by the reference angular size denoted by the angle theta. In rotational kinematics, we define the angle theta expressed in the unit radian as the ratio of the arc length over the radius. In optics, this theta is called the angular size, also expressed in radian, and is equal to h sub o over d sub o, where h sub o is the height of an object as perceived by the eye, and d sub o is how far the object is from the eye lens. The reference angular size, theta, is the angular size of the object when it is placed at the near point and seen without the magnifying glass. The near point is the point nearest the eye at which an object can be placed and still produce a sharp image on the retina. And for a magnifying glass held close to the eye, the angular magnification, capital M, is equal to quantity 1 over f minus 1 over di multiplied by capital N, which is the near point. In this equation, small letter f is the focal length of the lens, di is the image distance, and of course, capital N is the distance, the viewer's near point from the eye. So, let us now take a look at question number 1. A person who has a near point of 25.0 centimeters is looking with an unaided eyes at an object that is located at the near point. The object has an angular size of 0.012 radian. Then, holding a magnifying glass whose focal length equals 10.0 centimeters next to her eye, she views the image of this object, the image being located at the near point. Question is, what is the angular size of the image? We are given the near point, capital N, equal to 25.0 centimeters. The object distance, d sub O, and the image distance, d sub I, have the same magnitude, equal to 25.0 centimeters. The angular size of the object, denoted by theta, is also given and is equal to 0.012 radian. And the focal length of the magnifying glass, small letter f, is equal to 10.0 centimeters. And our target variable is the angular size of the image, denoted by theta prime. So we first compute the angular magnification, capital M, using this formula. Alright? So the formula simply says that capital M is just equal to quantity 1 over F minus 1 over di, alright, to be multiplied by the near point, capital N. Substituting, alright, we get capital M equals quantity 1 over 10.0 centimeters minus 1 over negative 25.0 centimeters, alright, and the difference, or that will be multiplied by the value of the near point, 25.0 centimeters. Alright, by the way, the value of di is considered negative because the image is a virtual image. Alright, so doing our math, we actually get 2.50. That is the result of multiplying 25.0 by the fraction 1 over 10.0 centimeters. Alright, and then 1.00 is the result of multiplying 25.0 centimeters by the fraction 1 over negative 25.0 centimeters. So we get the value of capital M equal to 3.50. Alright, so using the formula, capital M is equal to theta prime over theta, alright, we can now proceed in calculating for theta prime. Alright, theta prime is simply the product of capital M times theta. So that is 3.50 times 0.012 radian. Alright, that means the value of theta prime, alright, is equal to 0.042 radian in two significant figures. For the next optical instrument, we have a refracting telescope. Basically, it consists of two converging lenses, the eyepiece and the objective. And the length, capital L, of the refracting telescope is nearly equal to the distance that separates the two lenses. That is, it is approximately equal to the sum of Fe and F sub O, or the focal length of the eyepiece plus the focal length of the objective. Alright, the first image of a distant object formed by the objective is a real image formed inside the focal point of the eyepiece, right? And this first image becomes the object for the eyepiece lens. And then the eyepiece forms the final image at near infinity. All right? The final image is virtual and enlarged. So that brings us to question number 2. If the telescope shown in the above figure has the following specifications: f sub O equals 985 millimeters and f sub E equals 5.00 millimeters, find, letter A, the angular magnification of the telescope, and letter B, the approximate length of the telescope. The focal length of the objective f sub O is equal to 985 millimeters, while that of the eyepiece is f sub E equals 5.00 millimeters. And we are asked to find the angular magnification, capital M, and the approximate length of the telescope, capital L. So, computing the value of capital M using the formula, capital M equals negative FO over FE, right? That is, capital M equals negative 985 millimeters divided by 5.00 millimeters. Simplifying, we get the value of capital M equal to negative 197. So, we can now find the approximate length of the telescope, all right? It's just the sum of the focal lengths of the objective and the eyepiece. That is, capital L equals 985 millimeters plus 5.00 millimeters, or that is approximately equal to 990 millimeters in three significant figures. For our last question, the objective and eyepiece of the compound microscope in the following figure are both converging lenses and have focal lengths of f sub O equals 15.0 millimeters and f sub E equals 25.5 millimeters. A distance of 61.0 millimeters separates the two lenses. The microscope is being used to examine an object placed at a distance this of O1 equal to 24.1 millimeters in front of the objective. And the question is, find the final image distance. So, in the drawing, we have here the eyepiece and the objective lens. The object or specimen is placed on a slide mounted just below the objective. We also label here the focal points of the objective and the eyepiece f sub 1 and f sub 2 respectively. The objective forms a real inverted image, capital I, inside the focus f2 of the eyepiece. And the eyepiece uses the image, capital I, as an object and creates an enlarged virtual image, I prime, which is still inverted. So for our solution, the focal length f sub O of the objective is 15.0 millimeters, and that of the eyepiece f sub E equals 25.5 millimeters. The distance d sub O1, or the distance of the first or original object, is given as 24.1 millimeters. That is 24.1 millimeters below the objective. And we're also given the distance between the two lenses, okay, denoted here by d sub OE, that is equal to 61.0 millimeters. And our target variable is d sub I2, which is the image distance number 2, which locates, all right, the second or final image. So we first calculate for the first image, or di sub 1, okay, using the derived thin lens equation, that is d sub I1 equals the product of the focal length of the objective and the object distance number 1 to be divided by d sub O1 minus f sub O. Substituting, we get 15.0 millimeters times 24.1 millimeters, and their product will be divided by 24.1 millimeters minus 15.0 millimeters. So doing our math, we will get the value for d sub I1 equal to 39.7 millimeters in 3 significant figures. All right? So this first image formed by the objective will become the object, okay, of the eyepiece. And we label that second object distance, or d sub O2, okay, which is simply the difference between 61.0 millimeters, that is the distance that separates the two lenses, minus the value of d sub I1, which is 39.7, and that is 21.3 millimeters. All right? So this is the second object distance relative to the eyepiece. So we are now ready to determine the final image distance labeled as d sub I2. Again, using the thin lens equation that has been derived, that is equal to the product of the focal length of the eyepiece and the second object distance, d sub O2. And their product will be divided by d sub O2 minus the focal length of the eyepiece. Substituting, we get d sub I2 equals 25.5 millimeters, that's the focal length of the eyepiece, times 21.3 millimeters, all right, that is the object distance number 2. And then their product to be divided by 21.3 millimeters, all right, minus 25.5 millimeters, all right. So these are the object distance number 2 and the focal length of the eyepiece respectively. So finally, doing our math, we arrive at the value of the second, or the distance of the second image, this of I2, equal to negative 129 millimeters. All right. So this result, or value of this of I2, suggests that indeed the final image is virtual and enlarged and is located 129 millimeters below the eyepiece. So that concludes our tutorial. Till the next episode, mabuhay, mashallah. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.